For decades, the software world relied on the relational database, a rigid format of perfectly aligned rows and columns, locked together by mandatory joins. When applications using this structure get hit with massive traffic, the standard solution is vertical scaling. You upgrade the hardware limits of a single server host, adding more CPU and memory to handle the load. But a single machine can only get so large, especially when enforcing strict ACID compliance. These rules guarantee absolute data consistency across every transaction. But when a request pulls from multiple tables, the database generates massive CPU overhead to keep everything synchronized. When processing overhead piles up during a traffic spike, the rigid grid hits a wall, causing latency that hardware alone cannot solve. We saw this limit reached as global platforms like Amazon and Netflix began managing millions of concurrent requests every second. To survive, engineers shifted to horizontal scalability, or sharding, dividing the dataset across vast clusters of separate servers. But placing separate database pieces onto separate machines physically breaks the relational table joins. Standard SQL queries fail if connected data doesn't live on the same drive. This birthed NoSQL, an umbrella of specialized tools that abandoned the relational grid in favor of entirely new structural layouts. Surviving at this scale isn't about buying better hardware. It requires altering the physical geometry of the data to eliminate the bottlenecks. The simplest of these architectures is the key value store. Conceptually, it functions like a massive distributed hash table. In this model, the key serves as a distinct routing identifier, like a specific user ID or a session token. The database engine treats the value as an opaque blob. It stores the payload without inspecting or indexing what's inside, shielding the routing system from the complexity of the data. Because there are no relational joins to calculate, the system achieves O1 constant time complexity. This allows for instant data retrieval, whether the database holds 1,000 records or 10 billion. Amazon utilizes this architecture through DynamoDB to manage active shopping cart sessions. When you click your cart, pulling a single blob based on your ID is much faster than calculating inventory relationships across dozens of relational tables. By intentionally designing the database to be blind to the data's internal structure, engineers strip away the processing layers that cause delays in high-volume e-commerce environments. Another approach is the wide column store, like Apache Cassandra. Here, data abandons rigid rows to be organized dynamically into column families. Every individual data cell isolates 3 distinct elements: a name, a value, and a timestamp used to track exactly when that specific piece of data was recorded. Cassandra runs on a masterless peer-to-peer architecture. Every node in the cluster plays an identical role, meaning there is no central coordinating server to create a single point of failure. This design provides continuous high availability. If an entire regional data center crashes, the incoming data streams automatically divert and absorb into the surrounding active nodes. This append-only architecture allows Netflix to ingest a massive barrage of high-velocity telemetry logs, such as when a user pauses or rewinds a show. This columnar geometry easily digests a constant stream of sensor data, syncing it rapidly across servers stationed all over the world. Abandoning hierarchical master servers for peer networks allows systems to distribute massive volumes of data while remaining resilient. So, what do engineers have to sacrifice to reach this level of scale and speed? It requires moving away from the strict rules of ACID and following the base model, which prioritizes basic availability and data in a soft state. The core of this trade-off is eventual consistency. A data update might not be instantaneously accurate across every global node. For Netflix, your watched video timestamp only needs to be eventually consistent across regions to resume on another device. The modern internet does not run on perfectly rigid grids. It survives because engineers embrace flexible data shapes that trade absolute perfection for sub-millisecond response times across thousands of servers.